Well, we've made it to the final lecture. With this lecture, I'm going to focus on the Y variable taking on binary outcomes, yes or no, with parametric approaches, logistic regression, and non-parametric approaches, trees.
Here are some classification scenarios. A bank's interested in determining whether potential customers are creditworthy for a loan. The bank has a variety of information about each potential customer and would like to classify statistically the individual as being qualifying or non-qualifying. The director of personnel for a corporation would like to know which of a group of new trainees will be successful in a certain position at the company. The director wants to classify trainees into two groups, those who will succeed and those who will not. Businesses want to classify customers as returning or non-returning. All these situations are when the response variable is binary, namely yes or no. Other popular examples include success versus failure, win versus lose, buy versus don't buy, satisfied versus not satisfied, default versus don't default, and survive versus die. Ordinary regression works on the basis that the Y variable is a continuous variable. We will see in this lecture that ordinary least squares regression is not well suited for modeling binary outcomes, and we'll want to explore an alternative method known as logistic regression. Then we will proceed into the tree alternative called classification trees.
So let's do a simple example to bring out the notions of logistic regression. And we're going to consider a simple scenario where we have a binary Y and a numeric X. In particular, the Y is whether or not an employee is successful at a job task. 1 being yes, 0 being no. X is a score on a training test. The question is whether test performance is predictive of job task success.
Here are the data. We see Y taking on values of 1s and 0s, and the X taking on the test scores. Let's look at a plot of task against test scores for the employees. We see the Y variable in task takes on only two values in 0 and 1. If we were to plunge ahead and fit a standard regression line, we would get the line shown on the slide. Consider the situation where an individual gets 90. We could stick in that 90 into the regression equation and out comes a value of 0.6105. Considering the range for Y is from 0 to 1, it would seem that 0.6105 provides us with a predicted probability of success. That is, an employee scoring 90 on the test is associated with a 61.05% chance of having satisfactory job performance. However, there are issues with this regression fit that you can see visually, and let me indeed discuss with the next slide.
But there's a problem. What if the individual tests 80 on the test score? Well, if you stick an 80 into that equation, you're going to get a probability of success to the task of minus 0.0529. Well, that's obviously impossible. Probabilities cannot be negative. And if we stuck in the test score of 97, the probability of success would be 1.0749. Again, that's impossible. Probabilities cannot be greater than 1.
One possible fix is shown on this slide. Simply kink the line so it doesn't go negative or above 1. The problem with this solution is that it suggests that after a certain score, which is around 95, the chance of success is 100%. This is pretty unrealistic to believe that high score alone guarantees absolute success. On the other end, we surely don't want to believe that certain low scores means absolute failure. Furthermore, the kink is just too sharp. In reality, transitions are more realistically going to be smooth and not so abrupt.
So we're striving for something that looks like this. So we saw with standard regression, there's no guarantee that the predicted values will be in the correct range, namely between 0 and 1, unless complex restrictions are imposed somehow on the coefficients. A solution to this problem turns out to be to transform the probability to remove these range restrictions and model the transformation as a linear function of x variables. Now that sounds complicated. Let's try to demonstrate what I'm talking about. So again, our goal is to remove range restrictions, because if you think about, for example, the standard linear regression, it can extend out as far out and ever in one direction and far out forever and ever in the other direction. We want to get to that, and that will make our life a whole lot easier. The first thing we're going to do is move the probability of success, which I'll call PI, to what we call odds. Odds is a ratio of the probability of success to the probability of failure, as you can see here. Suppose the probability of success is 1/3. Then if we take the ratio, we have 1/3 divided by 2/3, which is 1 to 2. Now, I've written it here like a fraction, but we prefer not to do that because it can confuse us with probability. Many people like to write it as 1:2, which says for every 2 failures, we expect 1 success. Now, the languages of probability and odds are equivalent. If I tell you 1/3 probability, or I tell you the odds are 1 to 2, well, 1 to 2 is 1 out of every, 1 success out of for every 2 failures. Well, think about that. 1 success, 2 failures, that's 3 outcomes, 1 of the 3 being a success. Indeed, that's 1/3 again. Now, odds can take on any positive value. So there's no ceiling restriction, but it cannot be negative. So there is a floor to it. We're going to resolve all this by taking our friend log. It's going to be the natural log. And the log of odds is sometimes referred to as log odds or logit. This removes the floor restriction. In particular, as the probability goes to 0, the odds approach 0, and the logit actually approaches minus infinity. So there's no restriction on one end. On the other end, as the probability goes to 1, the odds approaches plus infinity. So does logit. So in the end, we have no restrictions on logit, and we can model the logit against an expression of x variables like we do in regression.
And here it is. We're looking at the logit, and we're modeling, in this case, something similar to a simple regression, namely a linear function of the x information. Now we can unwrap this by exponentiating both sides, doing some algebra, and ultimately finding that we have, in the end, a relationship between the probability of success and the equation shown above. We don't know beta 0 and beta 1. We're going to estimate them and in the end get estimated or predicted probabilities of success based on that equation. Now, how do we estimate beta 0 and beta 1? We use a paradigm called maximum likelihood estimation, which is going beyond the scope of this course. I'm just going to give you exposure and awareness of the idea. I'm not going to test you on it, but let me just walk you through a few slides. Let me define Fi1 as the probability of observing y equaling 1, given the x information. Well, that probability is indeed pi from the previous slide, and that's given by this expression. Let me also define Fi0 as the probability of observing y equaling 0, given the x information. And we see here that this is simply 1 minus the probability of getting a 1, which is 1 minus that expression above. All right, let's go from here. Assuming independence, the probability of observing a set of y outcomes would be the product of the individual probabilities. That's something I mentioned earlier in the course. For example, if the probability of observing y equaling 1 equals 0.6, then the probability of observing the values of 0, 1, and 0 is simply 0.4 times 0.6 times 0.4, which equals 0.096. This is called a joint probability. Thus, if we have n independent y observations, which can be either 0 or 1, the joint probability, which is referred to as likelihood, is given by the product of the n probabilities. Here I'm writing that with this expression here, with the big pi sign meaning product of those probabilities being the probability of being a 0 or being a 1, and in the end, when you multiply them all together, you get this joint probability, which I'm calling likelihood, or L for short.
Likelihood measures how well a set of data support a particular set of parameters. The key idea in maximum likelihood estimation is to find the values for beta 0 and beta 1 that give the largest likelihood. The value with the highest support, highest probability of giving rise to the data that we observe are called maximum likelihood estimates. These serve as our best estimates of the parameters.
The likelihood, being a product of n probabilities, can be incredibly small in value. Also, finding the maximum of a function based on a product is mathematically messy. So for both these reasons, it's customary to take the natural log of the likelihood, recalling that the log of a product is a sum of logs. We get the log likelihood, denoted by LL, as the sum of the logs of these probabilities, which will make life much easier. How do we find values for the parameters that maximize log likelihood? The answer in the end is to use mathematical techniques such as calculus or numerical methods. But before we let software do that, let's play a little bit and search by trial and error. Hopefully this will give you a better sense of the maximum likelihood idea. So I'm going to pick a couple trial parameter values. In particular, let me take beta 0 to be minus 49 and beta 1 to be 0.6. Let's now turn to the observed data. For example, consider observation 1. From the data table, you will find that observation 1 is associated with a y value of 1 and a test score of 96. If we were to stick in the value of 96 into this equation here based on the trial parameter values of minus 49 and 0.6, we find that the probability of success for a test score is 0.999815928. Now, if you go down the data table to observation 30, for that observation, y equals 0 and the test score equals 79. The logistic regression model based on the trial parameter values would give us a probability of 0.832018385 of getting y equaling 0 given x equals 79. Here are the two examples that we just did. Observation 1, where we see the outcome is y equaling 1 and the test score 96, and the model giving us the probability we calculated based on those trial parameters, and then we see the log of that probability. Here's the 30th observation where y equals 0 with a test score of 79 and the probability that the model gives of getting a 0, and we also see the log of that probability. We'll want to do what we did on the previous two slides for every single observation in the data set. If you get the product of all these probabilities down this column, you get this incredibly small value. If you take the sum of the log probabilities, you get this value here of minus 46.801733331. Now I rolled up my sleeves and tried various combinations of beta 0 and beta 1 and manually calculated the log likelihood values. We see the combination that we tried out of beta 0 equaling minus 49 and beta 1 equaling 0.6, and here's the log likelihood value we found. Log likelihood values are always going to be negative. We're finding the maximum value based on this grid. It's right here with a beta 0 value of minus 44 and a beta 1 value of 0.5. These aren't going to be the ultimate maximum likelihood estimates, but they're going to be near, because software is going to do this more precisely to finding to many decimal places on the beta 0 and beta 1. But for now, we can kind of feel or vibe that the estimates for beta 0 and beta 1 are somewhere around minus 44 and 0.5. Let's now turn to software to find these maximum likelihood estimates precisely. In JUMP, to do logistic fitting, the y variable must be defined as nominal. That means taking on a column of labels. In our application, success is associated with the value of 1, which in the end will be viewed as a label, and failure associated with the label of 0. Now, JUMP is not going to know what is success, what is failure, will not understand 1 versus 0 once they are turned to labels. So make sure you have JUMP realize what success is from what you deem success to be. Here's what I did. Notice that JUMP is viewing the y column here to be a continuous or numeric variable. I clicked on the blue triangle and changed it to nominal, and now it's viewed as a nominal, as you can see with the red bar icon. I went to fit model, gave the y variable, gave the x variable, and JUMP automatically realized that we're dealing with a logistic regression. Notice the target level I have here as 1, and that is because I view 1 as a success. And here's the output. Indeed, we see that we get the logistic curve that we were striving to get. JUMP will randomly jitter points. These are just artificial points. I'm not exactly sure why JUMP does this. It's a bit of a distraction in my mind. You can go to the red arrow option and uncheck the putting of points. We find below the parameter estimates. Now remember, this equation is an estimated prediction function of the logit. So what we have here is the log of the estimated probability of success over the estimated probability of failure equaling, and we see the values here, of minus 43.368442 plus 0.48972171 times x. As I showed you on a previous slide, we can rearrange all these and ultimately get an expression, a predictive equation for the probability of success, and here I show it. Like in regression, we can perform hypothesis testing on the coefficients. For example, for the individual x variables in standard regression, we use the t-test. In logistic regression, we use something called the Wald test or the likelihood test, as you'll see in the output. For testing several predictor variables simultaneously in regression, we use the overall F test. In logistic regression, we use something called the deviance test.
Let's talk about the deviance test. The testing of all logistic coefficients, regression coefficients as a group for all the x variables. And what the test is based on is the likelihood ratio test. Now recall earlier the use of the log likelihood, we'll call it LL, in the search for parameter estimates. Because the log of a probability is negative, the sum of the logs is indeed going to be negative, and thus LL will always be negative. Define deviance as minus 2 times LL. Well, you got a minus times a negative, you're going to get a non-negative number. And I say non-negative because you could actually have LL to be 0. How could LL be 0? That's the extreme case where the model fits the data perfectly. So each one of those probabilities for that we showed in the earlier spreadsheet, the probability of the outcome being 1 or 0, if that probability is perfectly predicted, those probabilities would be 1. The log of 1 is 0. If we add a whole bunch of zeros up, we'll get 0. So LL would be 0, minus 2 LL would be 0. So that's the most extreme case. That's kind of tantamount, like in regression, to have R squared being 1. And with that in mind, we can realize that when we add variables, as R squared approaches 1 in a standard regression, this is equivalent to, in logistic regression, minus 2LL getting closer to 0, the perfect case. The question is, if we add these variables, additional variables, over and above not having the variables in the model, do we significantly change the deviance?
Let us define D0 as the deviance of the model based on the intercept only, that is, no x variables in the logistic regression. Here, the null hypothesis would be that the betas for the x variables all equal 0. This is akin to a reduced model in a standard regression. Now define dm as the deviance of the model based on the set of x variables under consideration. This is akin to the full model in standard regression. As we add x variables, the deviance will always go down. The question is if adding the full slate of x variables will significantly reduce the deviance going from D0 to dm. Let us define the likelihood ratio test statistic LR as the difference, which will ultimately be the drop in deviances. So LR equals D0 minus dm. After replacing D0 and dm with their definitions, we find that LR equals 2 times parentheses minus LL0 minus LLM. If the null hypothesis is true, that all the betas for the x's equal 0, this statistic follows a chi-square distribution with degrees of freedom equaling the number of x variables in the full model. Here we could take a look at the output for the application under consideration. We see the minus log values under this column. In particular, here is minus LL0, 29.700593. Here is minus LLM, 15.584553. Twice the difference is 28.23208. This gives us the likelihood ratio statistic, which you indeed see here reported, and Jump notes it to be a chi-square statistic. And you notice the degrees of freedom is 1 because there's only one variable in the full model. The p-value is very small, indicating we have strong evidence to reject the null hypothesis that all the betas in front of the x's equals 0. There's only one x, so we're rejecting, in this case, beta 1 equaling 0. There's an r-squared value. It's a pseudo r-squared value. It's not like the regression in terms of how it's computed. It is a value between 0 and 1, and putting aside overfitting issues, larger is better. I will tell you, in most logistic applications, for whatever reasons, you're never going to see r-squared values greater than 0.9 for certain reasons. It does happen, but not as often as you'll see with regular regression. Just think larger is better. Again, putting aside overfitting arguments. We see below here tests individually for the x variable in consideration. Namely, this would be testing beta 1 equaling 0, but this is done through the Wald test, which is slightly different than the likelihood ratio test done above here. And we can see that because the p-value is not quite the same. Actually, the value for the p-value up here is the same as this individual test down here. So you actually have two different individual tests for, in this case, beta 1 equaling 0. The Wald test and the likelihood ratio test. The reason the Wald test is reported is because it has certain advantages and it can be used for testing one-sided tests. But all in all, we see the Wald test is giving us the same conclusion, strong evidence for rejection. Let's do some predictions. Suppose a person scored 85 on the test. We would stick in 85 into the formula that gives us the predicted probability of success. Here we stick in 85 into the B0 plus B1x formula. Remember that this formula B0 plus B1x is a prediction of the logit value, but we re-express it ultimately to give us a prediction of the probability of success. We find the prediction of the logit value to be minus 1.7420979. Taking the minus of that minus value, and be careful, that would be a plus, and then in the end you should be able to confirm you get a prediction of 0.149047 or 14.9%. We could have JUMP calculate the predicted probability of success. We simply go under the red arrow option and then choose Save Probability Formula. This will give us a dynamic data table. I typed in 85 and notice the value of minus 1.742097 we got on the previous slide, and then the predicted probability of 0.149 as we also got on the previous slide, and 1 minus this value would be the predicted probability of failure. And then JUMP has a column of the most likely Y. This is a classification. Based on the low probability of success, JUMP has determined the individual is to be classified as not being successful. We'll talk about how JUMP makes that classification soon enough. For a simple regression, the interpretation of B1 is straightforward. Change in Y for a unit change in X. However, in our case, the line that we have is affiliated with a Y variable being the log odds or the logit. If I were to change, for example, X by 1 unit, as you can see here below and color coded, the predicted logit value goes from minus 1.742 to minus 1.252. That change here is indeed the coefficient B1. So in summary, B1, it represents the change in logit or log odds for a 1 unit change in X. Change in log odds is hard to interpret. Let's exponentiate the log odds formula. This gives us the estimated odds ratio to equal e to b0 plus b1 times x. Let's now increase x by 1 unit. This will give us e to the b0 plus b1 times x plus 1. Doing the algebra, we ultimately get e to the b1 times e to the b0 plus b1 times x. Recognize that the second term here is equal to the predicted odds ratio before we changed x by that 1 unit. In the end, this means that e to the b1 represents the change in the odds of success for a unit increase in x. In our case, b1 equals 0.489727171, giving us a multiplier of 1.63186226. We found that for a score of 85, the probability of success is predicted to be 0.149047. So if we take that value over the predicted probability of non-success, we would find an odds ratio to be predicted to have value 0.175, which means 0.175 colon 1. The interpretation being for every 1 failure, there is 0.175 successes. It may be easier to move the decimal place over since odds can be interpreted proportionally. This would imply for every 10 failures, there is 1.75 successes. Based on what we learned, if we were to change the score from 85 to 86, that is an increase of 1 unit, then the odds ratio would change by this 1.63 multiplier. And when we do that, when we multiply it times the odds ratio for the score of 85, which is 0.175, we get 0.286, which means for every 10 failures, 2.86 successes. Now, it's a good exercise if you were to go back and find the predicted probability of success based on 86, get that p-hat value, divide it by 1 minus p-hat value, and find that you get the same value here of 0.286. Let's talk classification. In default, software classifies success based on a predicted probability greater than or equal to 0.5, and thus failure for a predicted probability less than 0.5. This threshold cutoff can obviously be changed. Here's the jump classification based on the default threshold. For predicted probabilities greater than or equal to 0.5, we find a classification of success or 1. For predicted probabilities that are less than 0.5, we see the classification of 0. Now, the model is not going to perfectly classify the results, just like regression will not perfectly predict. We have some difference between observations and what is predicted. In regression, that was called residuals. Here we see, for example, let's look at row number 19. The individual scored an 86 on the test. The predicted probability of success is 0.22. Jump classified this individual as not being successful. However, the individual was successful. let's look down here. Here are some predictive probabilities that are greater than 0.5. Jump classified these individuals as being successful, but they turned out not to be successful. I've highlighted the mismatches. You'll see that there are 7 cases out of the total of 43 that were misclassified, thus a 16.28% misclassification rate. And indeed, this is what JUMP reports under the fit details of the logistic regression.
Okay, so based on this threshold of 50%, the model has misclassified 7 individuals out of the 43 to have that 16% or so misclassification rate. What it doesn't tell us, that 16%, though we can look at the previous slide and see the breakdown, but it doesn't tell us that aggregate value, the type of misclassification, namely classifying as a 0 but the person is a 1, or the classifying as a 1 and the person is a 0. That's the finer details that we want to get at. And that is reported in what we call a confusion matrix. What a great name. I mean, statisticians are not the best at branding. Here I am as a professor teaching you statistics, and the last name I want to have for you is a confusion matrix, but that's what it's called. And we get at the confusion matrix through the red pull down. Here we see it. And let's choose it and see what we get.
Here's what we get. We get a matrix of counts and a matrix of rates. Let's take a look at the counts. On the columns, we have predicted. On the rows, we have actual. Consider the case of the actual observation being 1. There were 23 cases of that occurring in the data set. Of those 23, 20 were predicted to be 1, while 3 were predicted to be 0. We can compute what's known as true positive, which is the percentage of ones correctly classified as ones, and that would be 20 out of the 23, which equals 0.87, and that's the value you find below here in the matrix of rates. This is referred to as sensitivity. Another measure we can compute is true negative. This would be the percentage of zeros correctly classified. How many zeros were there in the data set? We can look on the 0 row here, find that there were a total of 20, and 16 out of the 20 were correctly classified as zeros. This would be a rate of 0.80, and this is referred to as specificity. We can now compute the false rates. For example, there were 20 zeros in the data set. 4 of them were predicted to be ones. This is referred to as a false positive. We thus have 4 out of 20, which is 0.20, a 20% false positive rate. You'll note that it's by no accident that 1 minus 0.80, which is 1 minus specificity, will give us that value also. In terms of the false negative rate, there were 23 ones, and 3 of those cases were classified as zeros. That would be 3 out of 23, or a false negative rate of 0.13, which is the same thing as 1 minus sensitivity. I'll note here that this breakdown are the values on the diagonal here, and thus we see there is a total of 4 plus 3, or 7 total misclassifications, which is what we saw earlier in aggregate. We saw the classification performance of the logistic regression based on a 0.5 threshold. What if we tried different threshold values, which I'll denote by S? By trying a range of S values, we can get the bird's eye overall view of the performance of the logistic regression in terms of classification. Now, this will ultimately lead to something called the ROC curve, which jump gives automatically with a click of a button. But I want to give you the behind the scenes idea of the ROC curve by doing some manual computations. I'm going to take the data table and sort the rows from highest predicted probability of success down to lowest. And I'll use these values as my S values. Consider the first case. The predicted probability is 0.994. An individual getting a predicted probability of 0.994 or bigger will be classified as a success. There's only one individual that has that predicted probability of success, so we will classify that individual as a 1. As it turns out, that individual is a 1, so we have correctly classified this one as a 1. There are 23 ones in the data set. The other 22 ones will be classified as zeros. Thus, you can see here the tallies. We have a true positive of 1 for that one individual, and we have a false negative tally of 22. There are 20 zeros in this data set, all of which will be classified as zeros for this high threshold. Thus, we will correctly classify all the zeros as zeros, so we have a true negative of 20. Finally, none of the zeros will be classified as a positive, so we have a false positive count of 0. If we take the true positive count of 1, out of the 23 ones, we get a true positive rate of 0.0435. If we take the false positive count of 0, out of the 20 zeros or non-successes, we have a false positive rate of 0. We can then progressively move down these S values, and obviously these counts will start shifting. You can confirm them for yourself, and it's a good exercise. But in the end, we'll get a false positive rate and a true positive rate for each of these S values. And I'm going to plot one against the other on the next slide. Let's now plot true positive rate versus false positive rate. The plot formed is called a receiver operating characteristic curve, or ROC curve for short. It provides us with an overall perspective of how well the model is for classification. For each threshold, and I've labeled a few along the way, we're plotting true positive rate versus false positive rate. I'm using a legacy plot called an overlay plot. I could have equally done this in Graph Builder. It's just a Y versus X plot. And here's what we get. Now the question here would be, is this a good ROC curve? Is this a poor ROC curve? Let's consider this question. So what is a good versus a bad ROC curve? To gain insight, I randomly generated data for an X variable called random data. Clearly, random data should not have any significant discriminatory power for classifying the Y variable. It's junk data in the end. When I ran a logistic regression on random data, I got an ROC curve that is shown here in red, which is pretty much hugging along the 45-degree line, which is suggesting to us that ROC curves near the 45-degree line are poor ROC curves. Let's think a little more on this. Suppose I took a coin and simply classified individuals as being a 1 if I got a heads and a 0 if I got a tails. That's clearly a dumb classifier. But realize that for the ones in this data set, there's a 50% chance I will correctly classify them as a 1. So the true positive rate will be 0.5. For the zeros, there's a 50% chance I will classify the zeros as ones. So the false positive rate would be 0.5. The combo of true positive, false positive would be 0.5 and 0.5, which would be a point right on the diagonal. And this is for a bad classifier. What about a bias coin? What if the coin has an 80% chance of coming up as a heads and 20% chance of coming up as a tails? You can go through the same logic. The ones in the data set have an 80% chance of being classified as a 1, so the true positive rate will be 80% or 0.8. And there's an 80% chance that the zeros will be classified as a 1, and thus the false positive rate would be 0.8, which again is a point right on the diagonal. Thus, in the end, a random or dumb classifier should be the diagonal ROC. Here's a side-by-side comparisons. For the junk data, the ROC curve is near the 45-degree line. For the data that we used, the test scores, which were legitimate data, there was some traction in that data in terms of predicting success, and that's reflected in the ROC curve moving away from the 45-degree line and moving towards this upper corner. Here is a visual of ROC curves from bad to better to better to perfect. A perfect classifier would have a 0 false positive rate and a 100% true positive rate, which would be right in this corner. In general, we're not going to have a perfect classifier, but the idea here is for a given true positive rate, let's say here at 75%, we would prefer an ROC curve that has a lower false positive rate, which the blue line will give, versus the green line will give a higher false positive rate. When you think of it from that perspective, you again understand why it's better to be moving in the direction of the corner.
Now, no one's going to construct ROC curves like I did, namely sort the predicted probabilities from largest to smallest, make a tabulation of what is a false positive, true positive, line by line. I mean, that's just to give you an understanding. We can go straight at it with an option here from the red arrow pull down and get our ROC.
Here's the ROC curve that JUMP produces. It's the same curve that I produce, it's just cleaner looking. JUMP reports something called an AUC, which stands for area under curve, and the value is 0.9087. How do we interpret AUC? Well, we interpret it as bigger being better. Consider a 45-degree line. Consider the fact that this box is 1 by 1, so the total area of the box is 1. For a bad classifier at 45 degrees, the area under it would be 0.5 or half the box. As we move toward this corner, the area under the curve moves toward being 1. Thus, a perfect classifier would have an AUC of 1, a bad classifier an AUC of 0.5.
Okay, so that's the idea of fitting a logistic regression, the idea of classification, confusion matrices, ROCs, and AUCs. Let's get at a meatier example. What I have here in this file is a data set on 5,000 bank customers, and the response variable is whether or not an offered personal loan was accepted from a previous loan campaign. So the bank has offered a personal loan to their customers. They've recorded whether or not the customer has taken this personal loan offer or not. And what they want to do is see if they can predict whether customers moving forward will take a loan or not based on the information they have on these customers, like the age of the customer, number of years of professional experience, the income, family size, average credit card spending monthly, education level 1, 2, 3, presumably something like high school, college grad, the size of their mortgage, whether they have a securities account, whether they have an online account with the bank, or whether they have a bank credit card with the bank.
With the first logistic model example, we only had one X variable, so there wasn't an issue of looking at various combinations of X's for model selection purposes. As we had in multiple regression, we have some options for model selection. If we don't have a lot of data, we can use AIC or BIC on the full set of data to find an appropriately balanced model. If, however, we have enough data and our goal is indeed prediction, we could do a data split of training versus validation. We can apply lasso with training and validation. Now, JUMP doesn't offer k-fold cross-validation for the logistic regression, but there's enough in JUMP for model selection that we can indeed proceed ahead. Given we have 5,000 observations here, I'm going to data split. I did an 80-20 split. I used the random seed of 709. Again, that seed is your own choice, just as long as you communicate that to the readers. I then proceeded to create indicator variables off the education nominal variable. We do indicator variables in logistic regression as we do in standard regression. Gave the validation column here, gave the take variable as the y here, and went with stepwise.
When we click OK from the previous slide, we'll see the following. We'll see the stopping rule is a maximum validation R squared. That's because it realizes that we are trying to find the best possible model in terms of performance on the validation set. It's using an R squared that is based on that thing I alluded to earlier, a pseudo R squared. We're not going to overthink it. Just realize that JUMP is trying to find the best possible model for doing the best on the validation data set. I click go, I'm using a forward, and it picks these variables that are checked off. And there are 8 of them. From the previous slide of the stepwise output, I'm going to click the button Run Model, which is going to give us a fit of the logistic regression model based on the training data. The reason I want to do that is I want to then fit other types of methods to the training data and compare them on their performance on the validation data. So when we do that, we get this estimated logistic regression model. There are options. I can look at the confusion matrix, and you can see here the performances in terms of classifying the yeses and nos, predicted versus actual on the training and validation. We'll want to compare this performance later when we consider other methods like trees.
The lasso method can also be applied to the logistic regression setting. Here I give the same variables. I give the validation column. You'll note here that you will pick, as I did in the past, the generalized regression for lasso. What JUMP will pop up is this distribution of binomial. That's associated with the fact that the y variable is either 0 or 1. I'm not going to go further than that, but that will be the appropriate selections in terms of personality and distribution for a lasso fit. Here is the lasso output. You'll see one of the indicator variables got zeroed out. That's because we could only choose 2 out of the 3, but what got zeroed out based on the lasso's penalized objective function is age. We can save the prediction formula from this fit to ultimately compare it against logistic and the tree methods that I will be also implementing.
So let's actually now talk about trees. We learned a variety of regression tree methods, a single tree, a random forest, a boosted tree for predicting a numeric Y. Now the same ideas can be applied to a categorical Y. And when we are predicting a categorical Y, it's called, instead of a regression tree, which we saw earlier, it's called a classification tree.
Now, my coverage here on classification trees will not be as in-depth as I did with regression trees. I'll give you the basic metrics and ideas behind classification trees, and then we'll just focus more on the implementation using JUMP. Let's start out with a small data set. We have here the variable we're trying to predict is whether or not an individual owns a riding lawnmower. We have information on the individual's income in thousands of dollars and the size of their lot that they own.
Now to get a feel for the data, what I'm going to do is plot lot size versus income and color code the points based on ownership. So in Graph Builder, all I did was drop the ownership column into overlay or color. Either way would work. The red points would be owning a rider mower, the blue being not owning a rider mower. And we're going to basically try to develop rules that will enable us to better determine whether the customer owns a mower or not. And remember how trees work. We're splitting the predictor space at values. So what are we doing with classification? What we want to do is try to find a split, either on income or lot size in the first round, that will give us what two regions that are what I would call more homogeneous, more pure, in the sense that they're more dominated with one color or the other.
Like with regression trees, classification trees will consider all split points on all possible values of all the X variables in consideration. Here, this would mean software would consider on lot size all the possible splits. Visually, that would mean drawing horizontal lines at each possible value of lot size and doing vertical lines at each possible value of income. After doing an exhaustive search on all those splits, software will pick an optimal split that gives the two most homogeneous regions. We'll see that JUMP will pick for this data set at the first step a split of income greater than or equal to 85.5 versus income less than 85.5. You see visually that for income greater than or equal to 85.5, which includes this point on the line, all the points are red. That means all the points are owners of riding mowers, while in the left region, it's mostly non-owners. The question now is, what should be the next split?
Okay, we've seen the visualization. Now let's talk software. Different software may use different measures for splitting, but they're all based on the same principle, namely coming up with some measure of impurity. What software will do is take an impure region, a mix of yes and no observations, find a split that results in two new regions which give the greatest reduction of impurity between the parent node and the aggregate impurity of the children regions, R1 and R2. Let's look below here. We have the impurity of the parent minus, after the split occurs, the aggregate impurity between the two children. We'll sum up this aggregate impurity, look at how much of a drop there has been, and that's the impurity reduction. And we're going to look at different split points that will give us the greatest impurity reduction. Now I noted with regression trees that software will pick the greatest SSE reduction, but JUMP does a variation with regression trees that it looks for the greatest, it looks for the most significant SSE reduction. The same thing here. JUMP will actually look for the most significant impurity reduction.
The idea of impurity reduction is a universal idea in classification trees used across all software. The only differences you might find would be how impurity is measured. For example, in some software, impurity is measured by something called the Gini index, which is taking the rate of yeses in a given region times 1 minus the rate of yeses plus the rate of no's in the region times 1 minus the rate of no's. JUMP uses what's called a G squared measure, which is equaling minus 2 times, in parentheses, the number of yeses in a region times the log of the rate of yeses in the region plus the number of no's in the region times the log of the rate of no's in the region. Now remember, you can't take the log of the value 0. So if either one of these rates equals 0, we don't compute the log. We just delete the term straight out. Let's consider the extreme case in which a region is absolutely pure. For example, having all yeses, which would imply the rate of yeses equals 1 or 100%. What would G squared give us? It would equal minus 2 times the number of yeses times the natural log of 1. There will be no second term because that would involve taking the log of 0, which we can't do. So that is put aside. Don't overthink this. It works out just fine. The G squared is a legitimate measure, and the condition of dealing with the 0 case is a legitimate approach. Okay, we would get in the end minus 2 times the number of yeses times 0, because the natural log of 1 is 0, which in the end gives us 0. This implies a region has no impurities, which is indeed the case here with being all yeses. We would also get a G squared of 0 if all the observations were no. In terms of the Gini index, we get the same value of 0 through its index. The rate of yeses is 1, the rate of no's is 0, so we see over here we get 1 times 1 minus 1 plus 0 times 1 minus 0, and we get 0 in the end. Two different measures that are used in application. There's no universally accepted single measure, but I can tell you basically these measures will pretty much give you the same results. Okay, let's calculate G squared for our application. We start out with the initial region. There are 24 points in total on this graph. 12 points are red, which are the yes observations, and 12 points are no, which are the blue observations. G squared would be minus 2 times the number of yeses, which in this case is 12, times the natural log of 12 divided by 24, plus the number of no's, which is 12, times the natural log of 12 divided by 24, to give us a G squared value of 33.271065. Now let's consider what we have after a split of income greater than or equal to 85.5 versus less than 85.5. We get two regions, region 1 on the left and region 2 on the right. In region 1 there are 19 points in total. Of those 19 points, 7 are red, that means 7 are yes, and 12 are blue, that means 12 are no. G squared would be for this region minus 2 times parentheses 7 times the natural log of 7 out of 19 plus 12 times the natural log of 12 out of 19, giving us a G squared value of 25.00818. The right region are all yes, all red, meaning there are no impurities, implying a G squared value of 0. Thus, the reduction is from the 33.271065 to the aggregate impurity of 25.008178 plus 0. When you take the difference, you see the reduction in impurity is 8.26289.
Let's go to software and see how things are reported. I'm going to the partition under predictive modeling, choosing decision tree. We're going to do a single tree here. Own the categorical variable of owning or not, yes or no, would be my Y variable, and the X variables being income and lot size.
Here's the initial output. Notice that we have 0 splits initially. Notice also the G squared value of 33.27 we computed earlier. Jump is reporting a couple split candidates, one at income equaling 85.5 and another one at lot size equaling 20. Jump is reporting a G squared reduction for the 85.5 split of 8.26289 rounded, which is exactly what we computed on the previous slide. Jump is also reporting log worth values. Remember, the larger the log worth, the smaller the p-value. Since the log worth is larger for the 85.5 cut point, it is more significant reduction in impurity than the cut point of lot size equaling 20. Thus, if we click split, jump will split at that income equaling 85.5. We can choose the other split point if we wish, but I'm just going with what jump will decide to do. Here's the tree after the split at income equaling 85.5. You can go to the red pull down, find display options, and then show probabilities. This will give rates and predicted probabilities. The rates are simply the percentages of yeses and nos in that region. The predicted probabilities are basically adjusted rates to give better probability predictions. The adjusted formula is quite complicated, but basically the intent of the adjustment is to ensure that a predicted probability is never exactly equal to 0, which is a pretty unrealistic scenario. We find here for this node of income greater than or equal to 85.5, the predicted probability that an individual will own a riding mower is 0.9167, so it's a high probability. Compare that with individuals with income levels less than 85.5. The predicted probability is quite low that they will own a rider tractor. This makes sense. Higher income is associated with the ability to buy an expensive item like a riding mower. Let's see what happens when we split again. We see that the split occurs on the lower income node, namely incomes less than 85.5. And what comes into play is lot size. For larger lots within this lower income region, the predicted probability of owning a riding mower has increased to 0.7208. This, of course, makes sense. Even though an individual has a lower income, if this individual has a large lot, there's more grass and thus more interest potentially to have a riding mower. However, on this side, we have smaller lots, and the predicted probability of owning a rider mower has dropped down considerably to 0.124, which also makes sense. Individuals with a lower income and a smaller lot, there's not going to generally be a desire to purchase a riding mower. Recall the personal loan example from the logistic regression discussion. Let's use the same data but apply the tree approach to make classifications. I will use the same validation data set with the random seed of 709 so that we can make fair comparisons across all methods with the same validation data. I'm choosing decision tree. I'm giving take here as the y variable. I'm giving all the x variables, but notice I'm not using the indicator variables. I'm using the original nominal education variable. As we've discussed before with trees, we don't need to create the indicator variables. I'll go ahead and click OK. I then proceed to click Go, and here is the tree that is produced. Remember, the software is guided by out of sample or validation performance. In the case of jump, it's using maximum validation R squared. It finds the balanced tree to be one with 11 splits. You can see here down in the split history that the validation line in red here goes up, 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 namely the R squared validation goes up, 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 and then eventually peaks out and goes down. That peak point is after 11 splits. Here's the tree, and you can see the tree is taking advantage of several variables, including income, education level, family size, and all that. If you look at the end leaf nodes, you can see the predicted probabilities that individuals falling in those respective regions will take the loan.
We can get from that model a leaf report to look at the various conditions and then ultimately the predicted probabilities of yes and no. We can get, like in regression trees, column contributions to see which informations on the customers played greatest toward the predictive probabilities, and we can see this is a pretty obvious one: income, the next player, education, family size, and so on. We could save the prediction formula, which is a probability formula, I believe it's called, for comparisons with the logistic regression and the subsequent trees that I'm going to build in a second. We could see the various confusion matrices for this fit in terms of the performance on training and validation. We'll get back to that.
Here I'm implementing a random forest. For the loan example, I went with 100 trees in the forest. There are 11 terms in this example. Divided by 3 is approximately 4 terms using that rule of K divided by 3. I'm not going to try different hyperparameter choices. We'll just go with this. We're just getting a sense of how the random forest performs versus the other methods that we have done up to this point in time. We get an output. We can save the prediction formula. Here's the boosted tree implementation with 200 layers, 3 splits per tree, a learning rate of 0.1, and early stopping. Let's summarize. For this loan example, we made a training validation split. We used the same split across all the different methods. In particular, we fit a logistic regression, we fit a lasso, we fit a single tree, a random forest, and a boosted tree. I then went to Model Comparisons platform to get side-by-side comparisons across these different methods. We see for the validation data that clearly the trees are doing better when it comes to measures like RASE. They have lower values compared to the Logistic and Lasso, and also lower overall misclassification rates. Furthermore, we see the ROC curves for all these methods. Though the Logistic and Lasso methods are doing respectable jobs, the trees are really tucked up here in the corner, showing that they are doing significantly better jobs in terms of prediction. So for this application, one wants to run with the trees for making predictions.
Well, believe it or not, we're at the end of our data journey. You learned a lot from the classical statistical ideas of inference, p-values, confidence intervals, and hypothesis testing to a variety of modeling concepts, explanatory to predictive with modern slants of model selection through AIC, BIC, or data splitting, to the ideas of not only regression uh, in the context of cross-sectional to time series, to these newer methods of trees, regression trees and classification trees. So again, I hope you have gained from this course. If you're continuing on in your data analytics learning, I hope this serves as a foundation for going farther and farther and farther. Thank you for enduring, listening to me, and the best of luck in your next chapter. Thank you again.